Last time we started section 11.1, talking about some basic notions of geometry, and we had encountered different ways that we could describe lines, and in particular we had left off last time on skew lines. Skew lines are lines that are not coplanar. Is this the one that we left off on, guys? Yeah? We'd already done this one? And then the two coplanar lines are parallel if they don't intersect. All right, so let's take a look at some examples. Example number 1. Can skew lines have a point in common? Why or why not? Right. Yeah, and so the answer is no, and because then they would be coplanar. Well, the lines wouldn't be coplanar, but they would intersect. So this is no, because they would be intersecting lines. Okay, so they do not have a point in common because if they're intersecting, they're coplanar. That's Madison mentioned. Okay, second question. Can skew lines be parallel? No. How come, Brendan?
They're different planes.
Right. The very definition of parallel has the word coplanar in it, right? You should be really careful. It says they're not intersecting. Certainly, skew lines don't intersect, but neither are they in the same plane. So no, because they would be. That means they would be coplanar. Okay, very good. Another one. I'm going to let you guys fill this one in on your own, and then we'll see how closely our answers all match. All right, so the first one says, if 2 points are in a plane, the line containing them is where? So write down where that line containing them would be. The second one, a line and a point not on that line determine what? What do you think that they create or determine is the word that's being used right here? If you're not sure, just leave it blank. We'll get to it, I promise. The third one, 2 different parallel lines determine what? Would they determine? And the last one, 2 intersecting lines determine what? Okay, what did you guys put on A? If 2 lines are in a plane, the line containing them is where? Well, that would be a line segment. So not quite what we're looking for. Where would the line, I'm sorry, where would, the line containing them be?
It would be continuous past.
It's in that plane.
It would be in that plane. It would continue past and be in between both. So it would be in that plane. That's the most general way to say this. So this would be in the plane. Okay, so 2 points are in a plane, then the line that contains them is in that plane. A line and a point not on the line determine what? A plane. When we talked about planes originally last time, we talked about it taking 3 non-collinear points to determine a plane. So if we have a line, then it's got at least 2 points on it, right? I mean, obviously infinitely many, but you've got the 2 points on the line, and you've got some point that's not on the line, so it's not collinear with those others, so you get a whole plane out of that one too. So this one is a plane. 2 different parallel lines determine what? Well, they are coplanar, so what do they determine? A plane, right? They lie in the same plane, exactly. So they determine a specific plane. And what do 2 intersecting lines determine? A plane. What a fun question, right? Yeah, so all of these things would be sufficient information to talk about the fact that you're in one specific plane, okay? Because they all have the ability to talk about 3 non-collinear points. And that's what it takes to determine the plane. All right, so now let's talk about how planes and lines can be related, in particular planes compared to one another. So two planes can either be parallel or intersecting, okay? Parallel planes have no points in common, so imagine, and you can write this down as an example, the floor and the ceiling, right? If they extended forever, you know, as they are continuing outward in both all directions and so forth, they would never intersect. They're parallel planes. Intersecting are crossing planes. Obviously, they do cross one another, not like the floor and the ceiling. And when they cross each other in a line. And so a real easy visual one is if you take the ceiling and one of our walls, right? If you take our ceiling, you take our wall, they intersect right along this top kind of corner, if you will, of our room. It goes from one corner to the other, and it's a line. If it were extended, it would be a line in both directions. Now we're going to do lines. So a line can be blank to a plane. So this blank right there is a fill in the blank. We're not filling it in. It would be filled in with one of these three statements below. So a line can either be parallel to a plane, intersecting and contained in, or intersecting and not contained in the plane. So we'll talk about each of them one at a time. So parallel to a plane means it has no points in common. So you can imagine, say, the ceiling and the line that goes along the floor and the wall over here. The floor is never going to intersect the ceiling. We already said it's parallel, right? So that line that's inside of the floor, in fact, any line that's inside of our floor would be parallel to the ceiling. Okay? Intersecting contained in. The line that is contained in the plane, dividing it into two half planes. So imagine you have, again, our ceiling, and you have any one of these like lines that you can see where the ceiling tiles go, right? That's a line that's contained in the ceiling. So it is contained in it. You can talk about it splitting it into two half planes. That's what we were talking about last time, Brennan. You were asking that question. So you've got the plane to the right and the plane to the left of wherever that line is drawn. Or it can be intersecting and not contained in it. So again, I keep talking about the ceiling. I don't know why. I like the ceiling today. So we're talking about the ceiling, and then imagine the line that goes up along, say, this corner right here. Right? Goes straight up, crosses the ceiling in a single point, right? It's going to cross the ceiling, just the edge is what we're talking about, okay? Crosses the ceiling in a single point, but it's not contained in the same plane, right? It's not like the lines that are actually on the ceiling tiles that we're seeing. So this is a third possibility of how that line could correspond to or relate to a plane. There's three possibilities. All right, some lines very specifically are perpendicular. So perpendicular lines are lines that form right angles where they intersect. So I've got two lines written here, L and K, and the perpendicular symbol looks like an upside down T. So that says L is perpendicular to K. And you guys know what that looks like in two dimensions, of course. So this is line L, this is line K. And it creates a right angle where it crosses. That's perpendicular. A line can also be perpendicular to a plane if it is perpendicular to every line in the plane. Okay? So the picture that we want to go back to is our ceiling with that one line that goes straight up into the ceiling on the corner of our room. Okay? Every line that it crosses in the plane, it is perpendicular to that line. It's not perpendicular to all the other lines that it doesn't touch, but every line that it touches when it crosses, it's perpendicular to that. It forms that right angle. And then we've got two planes are perpendicular if any angle formed by a line in one plane and a line in the other plane is a right angle. So let's take our ceiling and let's take this wall. Okay? So if I take the ceiling and I take this wall and I take this line that goes straight up in here into the ceiling, it's perpendicular, right? If I take this line that actually crosses into the ceiling, it's perpendicular, right? So we've got perpendicular planes when they have that right angle, just like you've got, and you can see it. I mean, the right angle is right there at the ceiling and the wall where they meet, right? So those would be perpendicular planes. All right, moving on into some angle stuff. We mentioned already right angles a moment ago, so anatomy of an angle. An angle is formed when two rays share an endpoint. So we've got a picture down here. We've got ray BA right here, ray BA. We've got ray BC, and they share the endpoint B. The endpoint, the rays are called sides of the angle, and then the endpoint is called the vertex. And then the interior is the part of the angle that's between the two sides. And so it's, in our picture, it's shaded in that kind of orange color. And it would continue and extend. It's not just, it doesn't stop, but the picture, does. So that it would continue on as long as the angle would continue on, which is forever in that direction. Okay? So the interior side of the angle is the part where you measure when you talk about it being 30 degrees or something like that. That's the interior. And that's what we're going to do next, is we're going to talk about measuring those angles. So when we talk about measuring angles, angles first are named by either a number, a Greek letter, or the vertex, or 3 points for clarity. So, for example, this picture, we can talk about angle alpha. We can talk about angle beta. If in the place of where alpha and beta was, there were numbers, we could talk about angles 3 and angle 4, or whatever they were, okay? So we reference them that way. It just depends on the kind of diagram that you're looking at. They're referenced on all those directions. In this diagram, you could not simply reference angle P, because there are 3 angles coming out of angle P. There's this angle right here that goes from Q to P to R. There's this angle right here that goes from R to P to S. And then there's the big outer angle that's Q, P, S. So in this diagram, we could not use this one where it says the vertex of the angle. If I had used this one over here, we could have, right? There's only one angle in my picture right there. And when we're talking about the angles, unless there's a reason otherwise, we're going to talk about the measuring the angle that's less than 180 degrees. So we're not going to talk about, for example, measuring around like, another color. Measuring around like that. That's not what we're talking about when we talk about the angle. Okay, we're talking about the angle that is over here. So there's just one angle in this picture, but over here there's 3 separate angles. So the best we could do is we could use 3 letters to talk about this angle. So this can be angle QPR, or this can be angle RPS, or this can be angle QPS. It does matter that P as the vertex is the one that's listed in the middle. So when you're going around your angle, it needs to be in order. Consecutive matters with the vertex in the middle. 2 angles are adjacent if they share a common side. And so you see this picture has adjacent angles in it, right? What side do they share? PR. And it's a ray, right? It's ray PR that they share in common. So if they share that side in common and they have a common vertex, which this does, yes, they have vertex P, and their interiors do not intersect. In other words, the interior over here where it says where the beta is not overlapping somehow the interior where alpha is. Okay? So that happens on this as well. Those don't overlap or intersect one another. Then those are called adjacent angles. And adjacent just means like we do when we talk about adjacent anything else. It's next to, right? Beside. All right, so for the purposes of what we're going to do in this class, we're always going to be measuring our angles in either degrees or in degrees, minutes, seconds. So we're going to talk about degrees first. The most common measure for an angle's opening is the degree measure. There are other ways to measure degrees too. If you've taken any mathematics of pre-calculus or calculus, you might have encountered those. But what we're looking at here is degrees. So the notation for degree is that little circle in the sky. Looks like a little circle that's up elevated. Since a full rotation or a circle is 360 degrees, 1 degree would be 1/360th of a full rotation. Each degree can be broken down into 60 smaller parts called minutes. And that looks kind of like an accent mark or almost like an apostrophe, but straight. Okay? And then each minute can be broken down into 60 smaller parts called seconds, and you get the double mark. Now, we're not actually going to be measuring in this particular section which of it is. We're talking, though, next about converting between the two, okay? Converting between degrees and degree minute second format. So the first one we're going to look at is taking degrees and turning it into degrees minutes seconds. Okay, are you guys with me? Okay, so the first part is easy because the number that's before the decimal is the degree. So we are going to have 32 degrees. That part's the easy part. What we do next is we take the decimal value, the 0.46, and we multiply it by 60. So you might be like, well, where did the 60 come from? Well, take a look back over here. It says each degree can be broken down into 60 parts called minutes. So we're taking the portion of this that's called degrees, and we're figuring out how many 60s we can make out of it. So we're going to multiply it by 60. And what we're going to do is when we do this, we're going to get the number of seconds. So I'm going to do my 1 asterisk mark right here. This is going to tell us the number of seconds. So somebody grab your calculator, or if you want to do this by hand, you need to know what is 0.46 times 60.
2,700.
I think you might have done 32.46 times 60. We just want the 0.46
Oh, sorry, I
only.
moved the decimal.
Okay, what did you get?
27.6.
Okay, better. 27.6 like this. Excellent. So that's 27.6 minutes. If this had not had a decimal, we'd be done. But the 0.6 minutes means that we can keep going further and we can turn that 0.6, it's the minutes part, it's the decimal part of the minutes part, into seconds. But we do it exactly the same way. So we've got the 32 degrees. We now have the 27 minutes. And we're going to take that decimal 0.6 and multiply it by 60, because there are 60 seconds in a minute, kind of like our clock, right? So we have our 32 degrees. We have our 27 minutes. What is the 0.6 times 60?
36.
That is 36 seconds. So you got 2 hash marks. Oops, I missed my hash marks here. Put those 2 up there. And technically, I mean, we can leave the pluses in between there, but that's unnecessary notation. I mean, they automatically are added together. It would be like writing 32 plus 0.46 originally. We don't write it like that, right? So the answer is written as 32 degrees, 27 minutes, 36 seconds. And that is the degree minute second format of this particular number. So it's all about multiplying by 60s, okay? So if going into degrees, minutes, seconds is about multiplying by 60s, what do you suppose we're going to have to do to take degrees, minutes, seconds, and turn it back into a decimal representation of degrees? We're going to be doing some division. Now here's the cool thing. The 48 stays. That's not the cool thing, sorry. I preemptively said that. The 57 we're going to divide by 60. And the 36 is actually going to be divided by 60 squared. Why in the world am I going to divide that by 60 squared?
Because you got divided into minutes before you divide into seconds.
Right. If I were to divide it by 60, I'd turn it into a number of minutes. But I don't want it in minutes. I want it in degrees. Yeah? So I divide it by 60 again to go back into degrees. So it's like I'm trying to go from here to here. I divide by 60, but I'm trying to go all the way from here to here. That's 2 steps. In other words, if I were to do it just by 60, I'd only end up at the degree marker, at the, at the minute marker, and I want to end up all the way back at the degree mark value. So I divide by 60 twice. Or you can divide by 3,600, obviously the same value. Okay? So if I take 48 plus 57 over 60 plus 36 over 60 squared, some of your calculators will require you to do that in more than one step. Some of them can do it all in one fell swoop. What do you get? It's going to be 48 point something, okay? So if your answer is something besides 48 point something, there's a mistake being made. What are you going to get? I mean, it better be a lot because that's 57 minutes. That's almost a whole degree, right? It's almost 60.
I got 49.05.
It should be 96.
Yeah, I got 48.96.
48.96. Check yours again, Catherine. Did you find your error, Brendan? Okay, are we okay with this? Here's something I want to ask real quick. Who's taken in this class taken number theory? Have we done this before?
I feel like it's
Does anybody remember what we did this for when we did number theory? If you haven't had number theory, I'm not talking to you, it's okay. This is not prior knowledge information you have to have, but we do this in number theory for another reason. Mm-hmm. What do you have?
We did something with ratios.
Wasn't with ratios. That would have been proportional statistical reasoning. Yeah.
Oh, I spent a long time in your office and I was trying to figure that out.
Do you remember what it was, Lauren?
I just, I remember it has to do with like the placement of the number.
Mhm.
It was for,
Did you have an idea, Ashley?
was it maybe one of the methods for multiplying the number there in the boxes?
Nope. Nope. Good guess.
Was it like scientific notation?
Nope. Not scientific notation.
I don't
That's also proportional to statistical reasoning. It was in converting between bases.
That's right, yeah, because I was thinking I had to see something.
So basically, what base are we working in here? Base 60. So we're multiplying and dividing by 60. That's where you've seen this before. So some of you are going like, this sort of feels a little bit like something I've seen, but I don't remember what it was or why. That's it. This is converting between bases. This is a base 60 conversion. Okay, good job. The next thing we're going to do then is a base 60 addition or subtraction in this case. Okay, so we're going to take a degree, minute, second format of two separate numbers, and we're going to subtract them. And I'm going to write them sort of, you know, like you do when you're in very early elementary school, where they're written on top of one another, because we can line them up easier. All right, so some of you are remembering different methods for adding and subtracting, multiplying, dividing when I asked my question. I'm just going to use the standard method because not everybody's had that class and knows those different methods. So we're just going to start on the right-hand side and subtract. 24 seconds minus 21 seconds is how many seconds?
3 seconds.
3 seconds. So that one, no problem. In the middle, however, we have a problem. 37 minutes minus 57 minutes. What's the problem? I can't subtract directly, right? I just can't, right? So what do you do in addition when you can't, in addition to subtraction, when you can't subtract a number like that? You have to borrow. Now, normally with us, we would take this 89 and we'd mark it down to an 88. We're going to do that here too. We're borrowing a degree. But how many minutes is 1 degree? 60. So when I borrow here, I'm borrowing 60. So I'm borrowing 60 plus the 37 I already have. How many minutes do I now have? 97. So this 37 is now 97. Can I now take 97 minutes minus 57 minutes? Sure can. What will I get? 40 minutes. And then can I do 88 degrees minus 48 degrees?
Yes.
Yes, what would I get? 40 degrees. So the answer is 40 degrees, 40 minutes, 3 seconds. So the only thing that you really need to be careful of here is to remember that when you're borrowing 60. The same thing would have happened if I had, say, for instance, 20 seconds minus 21 seconds, right? If I had to borrow from the column that has minutes in it, I'd have to borrow 60. I'd borrow 1, but they'd be 60 seconds because there's 60 seconds in a minute. Always borrowing from the column over is 60. There's a note on the bottom of this page, or this screen, and it's on, I think, your next page, actually. As long as your values for minutes and seconds are between 0 and 60, leaving answers in degree minute format, degrees, minutes, second format is considered simplest form for the answers. Okay? So keeping that in mind. So in other words, we don't want to leave something saying that it's going to be like 77 seconds. We wouldn't do that. Are you guys with me? So you're going to have a similar question to this one where you're going to do addition. And when you add them together, if you got 77 seconds, you'd have to turn them into minutes and seconds. Right? If you had 77 seconds, think even about a clock. What is that? Well, it's a minute and 17 seconds, right? Same idea here. All right, some different types of angles. I already mentioned one of the angles in a reference earlier. So these are the 4 types of angles. I'm going to give you just a second to jot them down first. So draw the 4 angles and then we'll label them. Okay, we're remembering that the blue part's the part that they're referencing as their angle. In all 4 diagrams, the angle is AOB or BOA, BOA, okay? O has to be in the middle. The first picture, do you remember what that angle's called? It's an acute angle. It's so cute. Yes, it's acute. It's an angle that's less than 90 degrees, okay? Between 0 and 90 degrees is an acute angle. I'm just going to go across the top. What's the second angle on there? On the top. They call it a straight angle. More commonly known as a line. That's how we usually think about it. But when we're working with angles, that name of that angle is a straight angle. How about the bottom left-hand corner? What's that one called? Right. That is a right angle. And a right angle is a 90-degree angle. A straight angle, I should have said, is a 180-degree angle. So right angle is a 90-degree angle. And what about this last one over here? It is obtuse. Now, I'm going to make mention of something just so that if ever in your future you hear it said, you'll be like, oh yeah, I remember we vaguely made word that we've heard that word before. There are references in some textbooks to the angle that would come around on the outside like this, like the angle that's more than 180. It's called a reflex angle, okay? But it's not consistently like in every book or anything like that. And this book that we're using doesn't use it. But just so that you're aware, there are some books that I have taught out of that will talk about that being a reflex angle. All right, circle. A circle, again, we've referenced this once before already too, but a circle, by definition, is the set of all points in a plane that are the same distance, known as the radius, from a single point, the center. So in this picture that's on here, O is the center, and there's infinitely many radiuses. I mean, you take the point O and go out anywhere on the circle and you've got a radius. But there are 2 radiuses on this diagram. What are they?
DO and OA.
Right, DO or OD and AO or OA, right? Those are radii, or radius. Each one is a radius. They are radii of the circle O. And then an arc is any part of the circle that can be drawn without lifting your pencil, your finger. So if you see up in blue on the top, there are actually 3 arcs in that blue section. There's arc AC, arc CB, and arc AB. And so that you have some notation for that, when we talk about an arc, whoops, let's use white. Let's say we talk about the arc AB on here. So if we were doing a segment, we put a straight line on the end, on the top. If we were talking about a line, we put the arrows on the end. If we were talking about an array, we put an arrow on one of them. For an arc, we draw an arc on top. Looks kind of like a halo or something, I don't know. It's like this curved line, which is terrible because lines aren't curved, but you know what I'm saying, right? There's this curved shape on top of it, and that's an arc. And there's nothing special about arcs being arc AB, the blue one. We could also talk about the arc AB that goes the other direction. So how do we talk about them differently? Well, here's the deal. Each pair of points in a circle actually determine two arcs. The shorter arc is called the minor arc. And sometimes it's labeled with only 2 points. So that would be like the arc AB that I just mentioned before. And it goes along the top. That's the part that's in blue. The longer arc is called the major arc. And whenever we talk about the major arc, we got to label 3 letters. No option of 2. So on arc AB, the major arc, what do you think we would call that with this diagram? With the things that are already labeled.
BDA.
We could. BDA or ADB. It doesn't matter where you start and where you end. But the idea is that you'd have to go like this, right? Instead of along the blue circle part. If the major and minor arc are the same size, they are called semicircles. Are there any semicircles in this diagram? There are actually. Not the ones I've already labeled, different ones. Name me 2 semicircles in this diagram. Yeah, DA and AD. I'll call the other one ACD just to designate. But the part that's dotted through the middle, the DOA right there, that line through the middle, which I haven't given the name to it yet, but it's diameter, right? That diameter, it's the top part, if you will, and the bottom part of those. Those create 2 semicircles. There's my diameter. A chord. A chord is a segment containing 2 points on the circle. So chords cut through the circle, right? You take any 2 points, you connect them, you have a chord. Specifically, if your chord goes through the center of the circle, like the one through O, right there on there, it's called a diameter. So you're going to have infinitely many chords and infinitely many diameters in a circle, right? Yeah. Every 2 points along the edge will determine chords, and some of those chords are diameters. All right.